Okay, so this is chapter 15, problem number 10. And it goes like this. Consider the following two-step process in which heat is allowed to flow out of an ideal gas that's held at constant volume so that its pressure drops from 2.2 atmospheres to 1.4 atmospheres. Okay, so all this is indicated on this pressure volume or PV diagram. So this two-step process, you've got this container of fluid or gas. It's held at constant volume, and heat flows out. So the energy goes down, the pressure goes down, and the system follows this trajectory in the pressure volume space. Okay. Then the gas expands while being held at constant pressure from a volume of 5.9 liters to 9.3 liters, and the temperature then regains or reaches its original value. So what I'm drawing here corresponding to this, and what they've also got on this diagram, is this curved line or curved curve is called an isothermal curve, and every point on this diagram, even though the pressure and volume are different, the temperature is the same. So in the second step, it's going from this condition to this final condition at 9.3 liters, but it's now reached its initial temperature that it had at point A. Okay. So then we're asked to do a few things. Part 1, or Part A, calculate the total work done by the gas in the process. And Part B, the change in internal energy of the gas in the process. And in Part C, the total heat flow into or out of the gas. So we've got our diagram. Let's think about the kind of concepts. We're dealing with thermodynamics, and we're thinking about pressure and volume, and we're thinking about change of energy, and we need to think about work. So there's a few equations and concepts that we need. First of all, the first law of thermodynamics. First law of thermo. That's the equation that tells you how does the internal energy of a gas or any system, but in particular in a gas, how does it change? It changes because of heat and work. We'll write that equation down in a moment. So that means we're going to need to think about work. We need to think about heat. And we're dealing with a gas, and we may want to think about ideal gases. Now, they don't say the word ideal gas, but in case we have to make any approximations, we may want to think about using the ideal gas law. Okay, so let's think about this then. What are the equations that correspond here? The first law of thermodynamics, that tells you that the change in the internal energy of a system, the thermal energy, if you like, it comes from there are two reasons why, at least in this context. One would be heat, which we represent with a Q, and the other would be work. And the way that we do this is change in thermal energy. Recall, this is the heat into the system, and this W is the work on the system. That's an important distinguishing. It is important to distinguish the work done on the system from by the system. This question is asking, what is the total work done by the gas in the process? And that's fine. Once we know the work done on the system, the work done by the system is just minus that, right? It's just a difference in wording. First law of thermodynamics. Okay, second of all, the work, W, is equal to minus the pressure times the change in volume. That assumes that the pressure is constant. Okay? Fortunately for us, the pressure will be constant in all the cases of interest, and then when it's not, you just have to do a little bit of calculus, but we won't have to do that here. We also might want to think about the fact, this is going to come up in a bit, that the pressure times the volume is equal to nKT. That's true for an ideal gas. And likewise for an ideal gas, the internal energy, or the thermal energy, involves the number of particles, n, times the average kinetic energy of each of those particles. So it's times 3/2 kT. In other words, 3/2 nKT. You realize that this n times 3/2 kT, that's almost like this. In fact, we could make it look like this if we multiplied by 2/3. So if you think about this, this 3/2, pull that out front, it's 3/2 times nKT, which means it's 3/2 times PV. That may or may not be useful. That should be enough to get us going. So part A, what is the work done by the gas in this process? In other words, going from A to B and then B to C. the work. So let's go ahead and write that. That's the work done from process AB. I'll write that like this. How much work is done from A to B, and then how much work is done from B to C. Good news is there is no work done from point A to point B because the volume doesn't change at all. Okay? The work involves a pressure and a change in volume. No change in volume, no work. Okay? The work done from B to C, what we need here is apparently, I'm going to put the minus sign in there, the pressure, which is 1.4 atmospheres, and then the change in volume, which is, it ends up at 9.3 liters, and it started at 5.9 liters. Okay? This is ultimately the work done on the gas. It's going to be negative. That's okay. The negative of that will give us the work done by the gas. Okay. As it stands now, though, this is kind of annoying because we have this in units of atmospheres times liters. This is minus 4.76 atmospheres times liters. Somehow, this is supposed to have units of energy. It does in some technical sense, but we want to convert this into units of joules, right? Work is a unit of energy. We want joules. So the thing to do is to convert atmospheres to the appropriate SI unit of pressure. It's pascals. So let's remember that 1 atmosphere is approximately 1.01, it's 1.013, I'll go ahead and put that in there, times 10 to the 5 pascals for every 1 atmosphere. And then a liter is 1,000 milliliters, and 1,000 milliliters, each milliliter is a cubic centimeter. So in fact, you can go ahead and write this as 10 to the 3 cubic centimeters for every 1 liter. And then finally, because we have centimeters, we want to convert that to meters. Let me get rid of all those factors of centimeter. We know that there's 100 centimeters for every 1 meter, and we've got to do that conversion 3 times. Okay. When all is said and done, this turns out to be approximately minus 480, and this should have the right SI units to be joules. The work done on the gas is minus 480. That means that the work done by the gas is minus this, in other words, plus 480 joules. Okay? That's part A. Part B. It asks, what's the change in internal energy of the gas in the whole process? In other words, whatever the energy at point A is, we want to say, what is the energy at point C, and subtract that at point A. So you could think about, all right, whatever that is, the energy at point C minus the energy at point A, that would be the change in energy. And we could try to compute that by figuring out the pressure and the volume, multiply by 3/2 and see what the difference is. There's a much easier way to do it, though. If I can convince you that the internal energy is the same at point A and C, then you'll realize that there is no change. So how can I prove that to you? I think looking down here, remembering that the internal energy is proportional to the temperature, assuming that the number of particles is fixed. When you recall that points A and points C are at the same temperature, that means that everything is the same. So I'm going to put here, but UA is equal to, we can write 3/2 NKT, whatever that is. UB is the same because these two temperatures are the same. These are equal. And that is what tells you that the change in energy is actually 0. If you don't like that, what you could actually do is you could use this, again, we would assume that it's an approximately ideal gas sitting in this container. Why don't we go ahead and do that with the longer method? UC, the energy at point C, this would be 3/2 times the pressure at point C times the volume at point C minus 3/2 times the pressure at point A times the volume at point A. And this should be approximately 0, at least to the extent that we've, to within a rounding error. Let's do this without converting all of the units. Let's just see what it kind of looks like. This would be 3/2 times the pressure at C, which is 1.4 atmospheres. The volume there is 9.3 liters. and subtract from that 3/2 times 2.2 atmospheres times the volume at A, 5.9 liters. And it turns out that when you do this, this is approximately, each of these terms is approximately 13. So I'm going to go ahead and write that as this is approximately 13 atmosphere liters minus 13 atmosphere liters, and therefore this is approximately 0. So if you like, you can do it this way, but this is probably the most straightforward way. The fact that they're at the same temperature is the key point. Finally, part C, which is the question of what is the total heat flow into or out of the gas. Okay, this is where we're going to combine many of the things that we've already used. So we figured out what the total work was, we figured out what the total change in energy is, and therefore what remains to be done is figuring out the heat. So using this first law of thermodynamics, what we can do is write the total change in energy for the whole process. We just figured out that was 0. That's equal to the heat that is added to the system plus the work done on the system. Recall, that's what we calculated before. Technically, that was the minus 480 joules. So using the first law of thermodynamics, we can figure out, therefore, that Q must be 480 joules.